In this video, we will discuss spatial operations in image processing. In this video, we will review convolution, sometimes called linear filtering, edge detection, median filters. In this video, we will show the one-channel representation, but unless specified, we can apply these operations to each channel independently. Spatial operations consist of a neighborhood. In this example, we will take a neighborhood of 2 by 2 pixels. We apply a function that involves each pixel in the neighborhood and output the result. We then shift the neighborhood and repeat the process for each pixel in the image. The result is a new image that has enhanced characteristics. These spatial operations take advantage of spatial patterns in the image. Convolution, or linear filtering, is a standard way to filter an image. The filter is called the kernel. The different kernels perform different tasks. Convolution is analogous to this linear equation. The input is the image x, output will be another image z. We have the parameter w. This is known as a kernel or filter. The star of this operation is the convolution matrix. There is actually an analytical expression for it, but it's a little confusing. So let's just go over an example to understand what's going on. Here's our image x. Here's our kernel w. It's just a smaller array. The array is made up of values that have been predetermined for some operation. Let's go over the operation of convolution. We start off in the top right corner of the image, and we'll overlay the kernel with that region of the image. We see the kernel values in red. We'll multiply every element of the image by the corresponding element of the kernel. For the first row, we'll get the following operation, multiplying the intensity value and summing the results. This process is repeated for the second row, multiplying the intensity value and summing the results. Finally, for the final row, we multiply the intensity value and summing the results. We sum those elements together. The result is the first element of the image z. We shift the kernel to the left, represented by the different colors in red. We multiply all the elements of the kernel with the image. This gives us the second element of the output image z. We'll shift the kernel one more column and perform the exact same operation, multiplying every element of the kernel by the corresponding intensity value of the image, adding them all together. This gives us the next value. We then shift the kernel down and repeat the process until we get to the end of the column, repeating the process until we get a new image. One problem is the images are different sizes. We can fix this by changing the size of the image x. We change the size of the image by padding. In zero padding, we add 2 additional rows of zeros and 2 additional columns of zeros. We can also replicate the values of the border. Low-pass filters are used to smooth the image, getting rid of noise. Consider the following image of a sphere. We have the following noise pixel. We can reduce the noise by applying a smooth filter or kernel. Smoothing filters average out the pixels within a neighborhood. They are sometimes called low-pass filters. For mean filtering, the kernel simply averages out the kernels in a neighborhood. Let's see what happens to the pixel intensities. To explore how the kernel affects different areas, we can plot the output image and its relationship to specific regions of this input. When we apply the kernel to this area of the image, the intensity values remain unchanged. Around the edge of the box, the values change as the values of 255 are averaged out with the zeros. Finally, when we get to the region with the noise pixel, we see the noise value as smaller. Comparing the original image and the output image, we see the intensity of the noise has reduced, but the edges appear less sharp. In general, there is a trade-off between sharpness and smoothness. In the lab, we will review several other kernels that explore this trade-off. Edge detection is an important first step in many computer vision algorithms. Edges in a digital image are where the image brightness changes sharply. Edge detection uses methods to approximate derivatives and gradients for identifying these areas. Consider the following image with a vertical and horizontal edge. Let's take a look at the intensity values. Let's plot on the first row of the image. The horizontal axis is the column index, and the vertical axis is the intensity value. If we move in the right direction from pixel 1 to pixel 2, the intensity value increases. In the image, we can represent this as a vector. In the same manner, when moving from pixel 2 to pixel 3, the intensity value decreases. We can represent this as a vector pointing in the opposite direction. The direction of the vector represents if the adjacent pixel is increasing. We can represent this change by applying the following difference equation, and this works by subtracting the intensity value of the adjacent columns j and j plus 1 in row I. This computes an approximation of the gradient in the x direction. In the following table, each row applies the equation to the intensity values for column 1 and 2. The final column is the result of using the equation. We can overlay the result over the image as vectors. We can apply the same logic to the next column. This time the values are negative. It turns out we can perform similar horizontal derivative approximations using convolution. The horizontal changes, or gradient, are computed by convolving the image with a kernel. These kernels are called Sobel operators. We can represent the output in the array of intensities gx. All the values are 0 except the elements corresponding to the horizontal edges. In this image, the gray values have different ranges where black is negative, gray is 0, and white is positive. These represent vectors we discussed earlier. We can use the same process to find vertical changes. This is computed by convolving the image with a kernel to get the image gy. This time the vectors point in the vertical direction. We can combine the output of each filter into a vector. If you are familiar with calculus, this approximates the gradient. Taking the magnitude of the vectors, we get the intensity values. We can plot it as an image that represents the edges. We can also calculate the angle representing the direction. Median filters are another popular filter. They are better at removing some types of noise, but may distort the image. The median filter outputs the median value of the neighborhood. Consider the yellow pixel. Consider the region in this 3x3 neighborhood. The resultant value of the output image is the median value of the 9 pixels. Depending on the padding, we see the median is identical to the image in most regions. In the region with the noise sample, we see the output is as follows. Overlaying the image values, unlike the median filter, we see the noise is no longer there, and the edges are straight, but the square is distorted as it's missing a pixel. Let's apply some spatial operations in OpenCV. PIL is relatively simple, so check out labs for PIL examples. We will create an image, new image, that is a noisy version of the original. First, we create a kernel for mean filtering. The function filter2D performs 2D convolutions between the image and the kernel on each color channel independently. The parameter values are in the lab. We see the new image has less noise, but the image is blurry. Image sharpening involves smoothing the image and enhancing the edges. We can accomplish image sharpening by applying the following kernel. We then apply filters 2D. Comparing the image before and after, we see it is much crisper. We can perform edge detection considering the following image. We smooth the image using Gaussian blur, a low-pass filter we will be discussing in the lab. This decreases changes that may be caused by noise that would affect the gradient. We can approximate the derivative in the x or y direction using the Sobel function. ddepth this is the output image depth, dx. dy is the order of the derivative in each direction. In this case, it will be 1. Finally, k-size, size of the extended Sobel kernel. We can output the gradients as images. We can approximate the magnitude of the gradient. We calculate absolute values and convert the result to 8-bit using convert scale ABS. Then apply the function add weighted to calculate the sum of 2 arrays and assign it to grad. We plot grad as an image. The areas with high intensity values represent edges. Check out the labs for more.